All right. Thank you all for coming in tonight. It's wonderful to have you all coming in. It's really amazing as to, we as being the Sydney's biggest AWS user group, we're starting to see people loop in more and more. So it's really, really lovely to have you all over here. Today, we'll be talking about serverless. Particularly, how we can power search capabilities by using serverless architecture. And for that, I thank Mr. Jesus Nunez, who's the director of Orinoco Solutions Private Limited. He has been kind enough to come and present us with the serverless architecture. He's with sort of a solution which can actually loop us to help in to power our search capabilities. Just a quick update on the deep recently. Now, for those of you who didn't attend our meetup last month, this is for you. So basically, AWS Sydney User Group has been selected to host the deep racing event. We are the biggest group in Sydney, so we get the advantage of doing that. So at this time, we are looking at the venues to host the event, and we'll be coming up with that news max to max next week or the week after that. But no, that's at the latest. But regardless, it's lovely to have you guys. I'm gonna push the ball to Mr. Jesus, and let's kick off and let's talk some tech today. Thank you.
Tech company with tech issues. So.
It's the same problem.
Would it happen, wouldn't it? I'm sorry.
It just happened earlier.
Yeah.
Now it just doesn't have to happen when the actual meeting is happening. So.
Yeah. Well, how did you fix that last time?
I think he's got a wiggle. I think he's got a wiggle in.
Yeah.
Alright. Let's allow it to be.
Yeah, I'm good. We can run straight to the TV, I'm sorry.
It's not just.
Apologies, guys. Sorry.
These will be here in a minute though, on the outside.
Yeah, we just literally
It's
tested.
flickering. It's flickering. We'll
So there's no
leave it to you guys.
We on one TV.
So while we're waiting for that, by way of introduction, my name's Anil Gupta. I'm the General Manager of Delivery at Polar 7. It was scheduled at the end of the event, just for me to announce, like Rockstar, they're hiring, we're hiring as well. So I'm looking for solution architects and service desk personnel. So there will be a slide that has an email address to contact, so keep it in mind, guys. Especially the Amazon guys who are already solution architects. All right, over to Jesus. Thank you.
Excellent. Thanks so much, Annie, for the kind introduction. And well, thanks everyone for coming along for this presentation. It's actually my first time in this meetup and in other meetups for quite a while in person. Yeah, so today we're going to be talking about serverless architecture, which is a topic that is sort of hot these days, and I'm hoping you will enjoy and learn something about it. So this presentation is about a real case study from one of my clients, and I'm going to go through the journey that how we took that client into implementing serverless architecture. A little bit about myself. I'm as Annie mentioned, the director or founder and of Orinoco Solutions. So we are AWS Select Partner, specialized in consulting. We are specialized in serverless, containers, data pipelines, and similar. Specifically helping small and medium businesses to either start a journey in the cloud or to modernize their existing applications. So who's the customer? The customer is Backup 365. They basically provide backup services for clients that have M365 data. And I think it's a bit controversial having data from Microsoft to AWS, but AWS provides a much cheaper solution, so that's why they use AWS. These customers they deal with MSPs, and that's how they bring customers into the platform. So we are talking about close to 3,000 companies, and that expands to 1.3 petabytes of data held in this platform. So one of the things they do is they back up the emails from these clients from the not AWS but the AWS platform, the Microsoft Exchange, well, similar to Exchange service. So they pull these emails and also SharePoint files and OneDrive files and so on. This particular use case is about emails. So the way they do it is they have an ECS cluster running on an ongoing basis, and that pulls information every 5 or every 10 minutes for all these companies. So they grab all the new data and they store it in this bucket, what I call the originals email. So that data then, so the bucket creates events per objects being created. That goes in an SQS queue, and then that gets processed in another ECS cluster that parses those emails, which are in binary format, and they convert those in text with the appropriate information to finally push it to OpenSearch, and so that users can search now using OpenSearch. So they have a portal where users can search for the emails and then request restores. So say, oh, I lost my account, or I lost some emails, so I'd like to see if I can restore these emails. They might search from dates or from specific terms in the subject, etc. Now, that looks all pretty good, that was working fine, but this is when the client contacted me and said, hey, we're having some issues with the current setup. The problem was they were spending a lot of money in OpenSearch, and that could be okay if you are using OpenSearch as it should. And in this particular case, they assumed that there were going to be a lot of searches, different clients interested in looking at things and then restoring and so on. But then after a couple of years, they realized, well, this is not happening. The data is just growing and growing and growing month over month. This business is not viable if you continue like this. So what about if we migrate to Athena? So they actually came with a requirement already, because they evaluated a few options. They said, well, maybe Athena is a good option. It's a most cost-effective way of doing searches, based on the observation that the searches were not that frequent, and the model of Athena, it charges per query, so it's serverless basically. So it's not a database sitting there. So the data all is sitting in S3, and Athena sits on top to do the searches. Who in the room is familiar with Athena or have used it before? Yeah, so quite a few people there. Nice. So I guess it's not going to be super strange for everyone. Yeah. So now so we were approached basically to fulfill this requirement. So it was a challenging thing because it was about to move all this data now into Athena and make it searchable. So so we needed to do that in a safety manner, and also to keep data consistency in a short period of time, of course, and cost effective. So what sort of architecture can we use to do that? Before jumping to the actual architecture, so we sat with the customer a couple of times in trying to define a plan and see how to move. So this is a roadmap with the phases that we implemented to do this migration. The first one, well, let's have a proof of concept to see if this actually works. We had lots of questions in terms of how to handle the data, the ingestion, the partitioning, and all that. So let's do that first in a staging environment with sufficient data that sort of simulates production. It's never the case, and you will see later that it's not the case. So after the POC was done, we say, okay, let's deploy the first release in production for new items. Now, this first release was going to cover the new data pipeline, but it will run in parallel with OpenSearch. We are not decommissioning OpenSearch first. It was just a matter of testing the water and see what is this solution really works, and start getting some data in the new bucket. The second phase was, once we're happy with that, let's say, okay, let's migrate the data now. So we move all the data, and once the data is migrated, we can turn on the feature to use Athena instead of using OpenSearch. And finally, once the searches were working fine for a selected internal number of users, we say, okay, let's flick the switch and decommission OpenSearch. So that's a sort of a high-level plan. So yeah, we did some analysis, and based on that, we make this proposition that to use lambdas to parse the image instead of a cluster, so that we handle like different peaks. So scalability would be better, probably most cost effective as well. That lambda will push the data to Kinesis data firehose. We chose Kinesis data firehose to facilitate data formatting, partitioning, compression, and it's a serverless service as well. Then Kinesis will put the data in S3 bucket properly formatted and partitioned, and then AWS Glue will then serve as a catalog, and also to run ETL jobs if we needed to. And finally, having Athena to enable the image search. So this is a high-level overview of the main services that were used. Yeah, before jumping into the actual architecture, we did an analysis on the data sitting there from this point of view. So the data was in binary format, as I mentioned before, so Microsoft binary format. There were around 2 billion emails there. The object size were between 1K and 2 megabytes, like very different, because some of the emails have attachments and so on. It was compressed. It was in a SIA storage class. And there were around 50,000 unique emails. So that means 50,000 email accounts, basically users in these companies. There were around, as I mentioned before, 3,000 companies. The input rate, so this is the rate as new emails were coming into the bucket, were around 15 per second up to 7,000 per second. Again, very different spikes, and it wasn't predictable. Sometimes they onboard new clients, and these new clients have thousands and thousands of emails that can happen at any time of the day, so you get a big spike. And to search for the emails, basically there was a predictable number of attributes. So the email, of course, the email date, they can look at ranges, email to, and subject. Maybe there was something else, but that's basically what they were using to search. Now, so this is an important part in terms of how the data was partitioned, because that will determine the performance of the query, but also how other systems were affected, in particular Glue and Kinesis firehose. So the first approach that we use is high cardinality. In this case, email and date were good candidates. We say, well, that's sort of producing too many partitions per year. The object size is going to be a little bit too small. It may affect the searches. But one of the big problems was firehose concurrent partitioning. So firehose runs from 1 second to 900 seconds, so up to 15 minutes. So it consumes data and then it does partitioning. But it has a limit. The limit can change, but by default it's 500 partitions in that block of time, which is very low compared to this approach. Could be increased. I can't remember exactly how the thing was, but these numbers were too high for that. So we say, okay, let's go medium, maybe email, year, and month. Still a bit better, but you still have a big number of partitions because it's based on emails. And then the lowest one was organization ID, which is a company-wide year and month. So even though it looks like, well, are you gonna be having those partitions for the whole company? We did some tests and the thing performed pretty well. So it wasn't as fast as the other approaches, but it was within the parameters that the customer could accept. And finally, we went down to something between 1,000 and 3,000 partitionings, concurrent partitionings processed by Kinesis. So we chose the last one based on those numbers. The data structure. So this is basically the glue table that we use, that we designed for the search. So we have the partition fields that I've mentioned before: organization ID, year, and month, and the other attributes of the email. I summarized some of the items here. So if you see on the right side, so that's how the bucket will look like. So using Hive naming convention, where you have the attribute and the value. So that table will basically be will point to that bucket to search for data. This is an example. Probably it's a bit too small to read, but what I just wanted to point out in this slide is that with this query, the result were there were more than 100 records in the result. Data scan was 6.6 megabytes and it took 1.2 seconds, so not too bad. And it only queued for 111 milliseconds. So that basically, this didn't apply for every single case because organizations vary in different sizes. Okay, so put it all together. So in this diagram, you can see the flow of the new architecture. So starting from the original buckets at the bottom, so that's the raw data with the binary files. Again, every time a new item, a new object is created, that will raise an event that will go to SQS queue. Now, this is where the new email parser comes in as a Lambda function and not as an ECS cluster that will read events from the SQS queue. I'll go in more detail in the next slide about that email parser, because this is sort of the heart of the system. So after processing that data, it will go to Kinesis. Kinesis does a partition, puts it in the final bucket, and then creates events for the partitions updated Lambda. So because you may have new partitions coming in, you need to update the partitions in Glue. So that's why that Lambda is there. At this point, well, all the data now is available to be searched. So if you see in the right-hand side, the portal user can then go through, well, they have a portal API. There's many layers in between, but they finally reached the new email search Lambda, which basically uses Amazon Athena API to retrieve data. Actually, you can with a pagination in place as well if you have more than 100 records being returned. Then Athena goes into that bucket, supported by the AWS table, and returns the data. Now, at the end, you see in the corner, inside, there is, so we created this scheduler to do file compactation. Basically, it's getting small files in bigger files for to improve performance. So that will run once a day, and for that day it will go in all partitions and try to make bigger files, but delete files and remove files, increase size of the files. Yeah, so as I mentioned before, the email parser is configured to receive records from SQS. I have some people asking me, well, so how do you do that? You poll events, is that like if you have a cluster? But with Lambda it's a bit easier, because you can configure SQS and event source, and then configure how many records you want to consume. Now, in the Lambda function, there's no code in terms of reading SQS, it's completely agnostic. So when you get the event payload in the Lambda, you can read the records. So basically, Lambda service is in charge of handling the delivery of events to the Lambda function. So for each object receiving the parser, it will do the parsing between, from binary to text. It will then create batches to push the data to Kinesis. So creating batches is more efficient instead of just calling one item at a time. Now it has a restriction of 1 megabyte of file, so I need to keep track of that. And we found that some of them actually went above that limit, and they were put in a dead layer queue for further processing with a different setup. So this was one of the sort of disadvantages using Kinesis data files. And finally, so we tag the S3 object as processed. So if we need to reprocess, or so it wouldn't get picked up again. All the moving parts were implemented as infrastructure as code. So I put a couple of examples here. Anyone familiar using CDK? Right? You guys? Okay. Yeah. For the ones that are not familiar with, is basically a way to produce CloudFormation in a programmatic way using either Python, TypeScript, or C#. I think it's right. So yeah, this is one example. This is how you configure, for example, the Lambda to attach the SQS queue and configure the batch size or the max batching window. So you can either, it's up to 2,000 or up to 3 minutes in this case, or whatever comes first. This is another example here. On the left, this is how you create a table in Glue, or how you configure a table in a Glue table in CDK. You specify the columns, the bucket that is pointing to the database, and on the right-hand side, the format, the partition keys. And the last one is an example of creating a Glue job in CDK. So as you can see, it's actually code. There's no JSON or YAML files, or Terraform files. So it's a program that someone can read and do stuff with. Now, so we talk about the data pipeline to ingest new objects and for them to arrive to Athena. So we needed now to do the migration. So we said, well, how do we do this? Should we use the same architecture? Should we change with something else? At the end, we decided to reuse the same architecture, which makes things much easier. So the only thing we needed to do was to traverse all the bucket and then create events to push it in the SQSQ. Now, traversing the bucket, you can do it in multiple ways. One of the most efficient ways is configuring that bucket to have an inventory bucket. So in the inventory bucket, you have the list of all the objects that you need to go through. And that inventory bucket could then be read as a table in Glue. So even easier. Then the only thing you need to do is read the table and then fetch the records with the object key, and that object key goes in the SQSQ, and everything flows as it was a new item. So we didn't make any change in the architecture. The only thing was to push those events there. We use a bookmark feature in Glue to mark these records read in case of reprocessing data. Now, until this, everything looks like nice. Or we put all the pieces together, but in production was a bit different. And what you can see here is there's a flat line going for a few days in some of these charts, but then there's a big spike. And I'll explain what is that. So in the first, so I requested Amazon to have I think 2,000 concurrent instances for Lambda, but it wasn't reaching what it was supposed to do. It was always between 300, 400, oscillating there. I spotted a few bugs in the parser, a few tweaks here and there, but then the things stay at the same level. Until I found out that the parser itself, the code that I was given to put in place to parse it was buggy, and it wasn't buggy, but it was throwing exceptions, like legit exceptions. I was throwing those exceptions, the Lambda, to get those events into the data queue. Now, throwing that number of events at a high volume is not good news for Lambda. Lambda doesn't like that, and it basically caps the capacity. As soon as we discovered that, we removed that throwing exception from the handler, and they just logged the key that wasn't processed for further processing. And you can see the spike is just going crazy. And in a matter of 2 days, the process was finished. So what you see there is 1,200 instances running for 2 days. So that was a lot. So yeah, on this side, you can see the red curve how it's going up and then down and then disappears. So that was a big learning in terms of working with lambdas and high volume of transactions, but also to understand that staging is not production. we tried a lot of stuff in staging, and we never had something similar. So yeah, at the same time, this is how the SQ was looking like. So we had like up to almost 4 billion messages in the queue, and it was going down slowly until the problem was fixed. The last drop that you see there is events that were expired, but there were duplicates anyway because we reran the process multiple times. So yeah, so you see 2 billion events lost. They went to the floor, but they were captured before. So we did capture the 2 billion rows that we wanted. So after the migration, so we can see the more normal behavior for new items. So that's the current load that happens in the email parser. We have some metrics here from Kinesis Firehouse after fixing the issues. And one of the relevant things here is the partition count, the left top. You can see it oscillates around 500 and then it goes up to 1400. So that's sort of the variations you have in the load. And these are basically partitions being handled by Kinesis in 15 minutes. Now, before this nice picture, we had a lot of partitions count exceeded. Okay, that was actually, I mean, we requested to AWS increase, but they asked for a lot of sort of justifications why you need more partitions until they finally gave us. But before that, we had around 20 delivery streams working in parallel to be able to cater for this load. And the other thing that improved was the per partition throughput. You see it's around between 200 or 400 K. So that's that basically produces much bigger files in the destination bucket. So what do we get at the end? Well, what the client was looking for was to optimizing code or reducing cost. So OpenSearch was decommissioned. That was a good savings. There were new costs, but they were around 1K. I would say maybe between 1 and 2Ks in certain scenarios. This is not counting the initial migration that cost some money, but it paid off in a matter of a month, I think. There's no infrastructure to maintain, so that's the beauty of a serverless architecture. There's no clusters or VMs, patching, all that stuff goes away. The migration was executed in a very short time, so we're talking about between 1 and 2 weeks. And then one of the most important things is that the email search functionality, it was working as expected. So what did we learn about this exercise? Well, I guess that the first thing is that getting everything up right from the beginning is pretty hard, especially when you're dealing with data that you are not sure how the data is going to behave. There's different sizes, different frequency. So it's a lot of trial and error until you tune, and get to the state that you want. Testing in production sometimes is better. I think it's getting more and more popular, I don't know, for the past 10 years. Still, certain institutions will get scared about it. But it's almost impossible, or in some cases impossible, to replicate that scenario in a staging environment, or super expensive. As I mentioned before, Lambda and Kinesis Firehouse were excellent. Now, a glue job for streaming would have been better. So I tried this with other data pipelines, and you can configure glue to receive streams as well. I didn't know much about this process, but then we learned about how to use it. That process would have we have done the partitioning, the formatting, compression, with no problems. We wouldn't have the some of the issues that we have with Kinesis. Well, that's today's talk. Thanks very much. If you have any questions, please feel free to shoot.
In the search filter, it mainly concerned about the timing of the email and where it's sent to and subject line, but it never touches the contents of the email itself. So can you change the search filter to include a keyword in the email contents?
The body
Yeah,
of
in body of the email. It will be a lot difficult, will take a lot more time.
That wasn't part of the requirement, but I think that's why they have the idea of using, or they had the idea, they implemented open search, maybe to do more free text search and stuff like that.
Yeah.
But they realized that it wasn't that common, so it wasn't there was no use case for that.
Oh, okay.
So they thought, oh, so we can do this analytics and stuff, but the need wasn't there. Yeah.
But is it possible?
It is possible, and you could use Athena to do that. It might not be the most efficient way. Maybe something like open session would have
But
been better.
in European data privacy standard, it probably would not be allowed. That is my understanding.
For privacy?
Yeah, yeah. That there is a legal hurdle in there.
But this data is managed, or this service is for the customer. So it's not, it's all encrypted and properly secure. So because even when they search, the results that they get, so they see all the content there. So they don't search in the content, but they can see the content.
What happens if an organization wishes to leave the service provider because his emails or his search keywords are all filtered all the way through lots of bits and pieces? So you've got to assure the customer that any of his customers that wish to withdraw from that email service, all the artifacts have been deleted, because otherwise they don't want things left in bits and buckets here and there. So can you do that easily?
Yeah,
with your model?
they have processes in place to offboard customers, or offload customers. Yeah, they delete all the data, so nothing remains there. Yeah, and I mean they have this system for a couple of years, so we just help with the sort of improving the current architecture. Yeah.
Yes, a question.
Yeah.
In this level of scale, optimization and performance obviously is quite significant. Did you get to do any sort of optimizations in Landers, for example, around allocation of memory, runtime, things like that, timeout? And if you did, then what sort of conclusions or insights?
Yeah, I would say all of them. So, I mean, we started with a sort of optimistic approach, where maybe 1 gig we carry for this. Then the Lambda was timing out a few times, even though it was at max. So then we redesigned the code to improve that. Yeah, so the changes were more around the design of how to capture. Actually, that number, yes, I remember now. That number, the 2,000 events in SQS, we played with that a lot, because in some cases the Lambda was taking maybe 30 seconds, but the throughput wasn't as high as I was expecting. I said, well, if we keep at this rate, it's going to take like 2 months to process all this data. So we need a way to crank up this. So we play with that in terms of CPU, memory, and the number of messages that were received. I'm sure that answers your question.
Yeah, it does.
Yeah.
And I'm also curious about the cost aspect, because I remember reading in some places that they talk about, for example, allocate more memory, it costs you more, but the performance of the Lambda is so much better than when you look at the big picture, it actually costs you less. So I'm just curious again, because at that scale, I'm sure that you reach those, situations.
Yes. So we did those analysis because if you get the Lambda running at a slow pace for a month, it would have cost a fortune. So we managed to reduce that to 2 days when finally it scaled. And yes, the costs went down.
Interesting.
Another question? Comments?
With the S3 bucket, did you actually have to end up paying for it? Because you said that Athena sits on top of it. So how does that actually work? Because I'm not really familiar with Athena.
Okay. Athena is a rebranding of the Presto database, which is what's developing in Facebook, and is an engine that is designed for big data. So basically, parallelizes process similar to Hadoop. Yeah. So in that sort of space. So the way Athena works is to find the schema of the data. It relies on AWS Glue. Okay, so Glue has the schema, the names and the location of the files, and then Athena looks into that and reaches the bucket. Now it does that in parallel. That's why the partitioning is important. If you have the right partitioning, it may spin up parallel processes per partition, and then do a MapReduce operation.
So you still have to end up paying for the S3 storage itself.
Now the Athena charges per query, depending on the amount of data. I mean, I don't remember, but I don't know. 1 terabyte is, I don't know, $10 or so. Yeah, someone?
All right.
Wait, one more.
Yeah, sure.
No worries. Go for it.
Athena queries. Did you find the performance, and again, talking about cost, satisfying to the point where you didn't need to cache anything? Just work all the time against Athena and it's all happy days, or did you find yourself caching results just to reduce costs or improve performance or whatever that might be?
Yeah, cost was never an issue because, and we monitored that for a couple of months, because the number of searches were not that high. Okay, so we never had the problem of that. Yeah, I get from the point of view is what sort of data can we cache? Can we have it like hot? We don't need to reach for the data. Yeah, we didn't get to that point. One of the basics that we did was to create those indexes. Without the index, it's pretty slow. So the beginning was like, yeah, but the partition have the why so slow? It's got the index. And yeah, the speed was much faster. Yes.
With 2 billion objects in S3, did you have to worry about object failure? No.
Object failure in
In S3, I sort of never really had to deal with this
Corruption,
myself.
maybe?
But yeah, object corruption. Like I thought S3 had a very, very, very low level of data corruption.
Yeah.
With 2 billion objects, maybe that comes up.
We never experienced that with that volume. Like I've never seen S3 failing.
Yes, I mean,
Yeah.
I remember seeing that there is a finite number on it. It was just very
Exactly, it's 11 nines or something.
something like that.
Yeah.
I think it's the 11 nines actually.
Yeah.
The 11 nines, right?
Yeah, 11 nines,
So 99.9999, 11 nines is the
What's 11 nines times not 2 billion?
Especially it's a petabyte as well, right? It's a petabyte of data, so there will be some errors in there.
Yeah. The more, but yeah, the 11 nines is the reliability, I believe. Yeah. 99.
It's good enough.
Sure. You want to talk about that, Jacob?
The statistics is like if you statistically lose, if you had like 100, something like 100,000 objects or 100, you'd lose one every million years or something like that. So there's like 6 copies made. It's completely right.
And that's statistically. Remember, the cloud's been around mainly for 20 years, so yeah.
It's like 1.4 petabytes is pretty good. That's in a petabyte club. You get like a special badge.
So everybody
It's not like
a
a-
refund.
It's not crazy.
Anyway, well, thanks very much for your questions. And
All right, thank you, Jesus, for the lovely and informative presentation. That was really thorough, to be honest with you, and thank you for that. We appreciate it. Hopefully, I nailed this. I didn't. I did.
Oh, now it's back.
I did. All right. So, all right, guys. As we said, we are from Pola 7 and we are hiring cloud architects and engineers. So please do reach out to us. And
No spam, no spam, please.
well, and again, though we are thankful for Rock for letting us host the platform. Even they are hiring, so please do visit them as well. And special shout out to Seth and Andreas. Thank you again. It's been lovely. Thank you for providing us food, and thank you for letting us host the platform. It's been wonderful. And guys, stick around. Have some pizzas, talk to each other. Network. It's an opportunity, and it's been lovely to have you guys. Thank you so much for coming in, and we are looking forward to seeing you guys next month again. Thank you guys. All right. Please help yourself for some pizzas. Go for it.
I don't think I've ever met you.